we will hit, and now we're ready. I'll go from current slide, and I guess we'll go from current, there we go. All right, and I may even turn on the projector today. Okay. The one announcement, and it sort of has multiple pieces to it. I think I did this last week, but maybe not all of you were here. Are any of you also in a first mini-term class? You are, okay. Yeah, I think I talked with Thomas last week. The first mini-term classes are ending either tomorrow or Wednesday. I think Wednesday, the 4th, and that would be Wednesday. Wednesday is the last day for first mini-term. Okay, what that means for first mini-term students, and well, it means a lot of things, your class is almost over, but one thing that they did late last Tuesday in the evening, they finally got around to opening student course evaluations. So those are open, so if you know of any student who's in a first mini-term class, please let them know the student course evaluations are now open, and please do the student course evaluations, okay? Now, the second ramification for that, meaning the second mini-term starts Thursday, the 5th. So if you're in a second mini-term class, be prepared to go to class on Thursday. But that also means for all of you that we are approaching our midterm progress reports, okay? And that means that all the instructors have to submit midterm progress reports, which means any student who has a D or an F at midterm, we have to report and let people know in counseling and other places, so then they'll be getting in touch with those students and seeing if they need help with tutoring, with transportation, whatever might be the issue, and trying to give them counseling and seeing if we can hang on to those students and get them to complete and get things done. So if you don't want someone bugging you about that, and all of you are very capable students, I need a score, okay? I think there's 10 in the class. 8 of the 10 have submitted something, okay? Either a research, I take that back. No one's submitted a research paper, okay? But 8 of the 10 have turned in your first test, which is great, and those scores have been pretty good. So I do need, besides Carla showing up, I do need a score from you, either your research paper or your first test, one or the other, or both. I'd love to have both. So please get me something that I can grade before or by Wednesday if possible, okay? If not, Monday would probably be okay because they usually give us about a week after the midterm to get those in. So try to get me a score, preferably by Wednesday, but definitely by next Monday. Or let's see, a week from that, I guess even next week, just anytime next week. Okay, so that's school-wide announcement. Here's a more personal type announcement. This is one of the strangest weeks I probably will ever have, and I'm almost near retirement, because today's fine. Tomorrow, however, I have a doctor's appointment. I think I told y'all at the first of the term that I have a mild form of leukemia, so I have to see my hematologist 2 or 3 times a year, okay? He only sees patients on Tuesday mornings. So therefore, tomorrow morning, I have the appointment. It's at 10:40, but I have to be there for blood work at 9:40. I have to be there an hour early for blood work, so I'm gonna have to leave campus by 9 o'clock. So that is going to wipe out most of my first class, all of my second class, and depending on what time I get through the appointment, it'll probably wipe out the first part of my third class, okay? My afternoon class should be fine, okay? But the first class will be terminated early, second class won't meet at all, and the third class will probably start late. But that means my office hours may be modified just a little. 8 to 8:30 will still be good tomorrow morning, and 12:45 to 1:15 should still be good as well, because I should be back from the doctor well before 12:45. So that part will be okay if you're looking for me tomorrow. But don't look for me between 9 and 12. Might be back before 12, but there's no guarantee of that. Okay. And that does lead to another issue that I hope I don't even have to say. Does anyone know what tomorrow is? Say again?
My grandmother's birthday.
Oh, that's it. Wait, you win the... No. Okay. It may be. Okay. It's also primary day. And I hope that every one of you are planning to vote. Please vote. If you don't know how to vote now, go home and get busy on it and make an intelligent choice tomorrow. Okay, polls open at 7 and they close at 7. I believe that's correct. That's what they've always been. It's going to be tight for me to fit that in. I'm going to have to leave here in plenty of time to get home to vote, because tomorrow morning I've got to be here early because I've got the doctor's appointment. So I will be leaving campus early. But please, folks, get into the habit of voting. Okay, it's your responsibility, your right, and we don't operate well if you don't. Okay, please vote. Okay, all right. That's paid political announcement. Okay. All right. Any questions on anything we've done up till now, including anything I just talked about? Okay. We're in chapter 3, differentiation. To me, the most important chapter in 125. Okay. We're in section 3.4, the chain rule. Almost through with this. We started in example 16 last time, but we did not finish. We did examples A, B, and C. We did not get to example D, or that's where I have my mark. Is that where everybody else had that we were? Okay? So here's where we go here. Now, this is a really weird thing, like they're showing way too much here. After rewriting the function below, use the logarithmic properties. So here's your function. Y is equal to log base 3 of square root of x over x plus 5. Okay? Now, what logarithmic properties are they talking about? Does anyone remember from last week? That was a long time ago. Okay? What can you do with that thing based on what we talked about last week? The log of a quotient is the... Please help me, somebody. Well, I forgot to say too, we're finally getting some rain. That's so good. No, never mind.
Log of the numerator minus log of the denominator.
Okay, is the difference of the logs of the numerator and denominator. Very good. How about the log of a radical? Can you even do that? Probably easiest to rewrite that as the numerator what is the square root of x in exponential notation? Second? X to the 1/2. And what's the log of a variable raised to a power? Anybody? Good boy. Last week was a long time ago. What's that? Okay. Remember I talked about the hierarchy? The lowest level is adding and subtracting. The next level up is multiplying and dividing. The next level up is powers and roots. Okay? And what a log log does for you is drop you down one level. So if you're taking the log of an exponent, what does that do? It lowers it to a multiplication, okay? And that would be 1/2 the log of x. The log of x to the 1/2 is 1/2 times the log of x, okay? So with that in mind, that's how they can do the second step. 1/2 of log base 3 of x, that's your numerator, minus, because it's the denominator, the log base 3 of x plus 5. Okay. Now, the other issue here, now that you've done the part that deal on the logarithmic properties, now we need to deal, and by the way, what we're doing is differentiating, but this is a different. Here we had a log base 10, here we had ln's, log base, the natural logarithm. And just like we did here, when we take the derivative of the log base 10, you take the derivative of the inside here as normal, okay? But you have in the denominator log 10, okay. Derivative of log is 1 over the thing. So that's where the 1 over cosine comes. Chain rule part gives you the numerator, but you also, because it's a different base, you have an ln 10 down here. Now that's just a number, okay? And that's how we dealt with this one. So based on this, as a hint from last week, since it was up here, what would we do here? I'm going to write it above it because I don't have room to write below it without getting into problems. Okay. Oh, look at this. We have, well, not quite perfect attendance yet, but close to it. With Houston here, right? Under the hoodie and stuff. Okay. So all we're missing, who are we missing? Devontae. Okay. I hope I put you in the right place. Yeah, Devontae's missing. Okay. All right. Now, of the announcements I made before, go back and listen to them on the YouTube videos, but I will repeat this one. You know what tomorrow is? Excellent, okay? And it's also Cal's grandmother's birthday, okay? So we've got 2 excellent answers there, but what else that you have some responsibility in? Oh boy, tell them, class. Primary day, vote. Plan to vote, 7 to 7, okay. All right, let's move on. Based on everything we just said, how do we take the derivative? And that's what we're doing here. You can write this as y prime is equal to, and what's the derivative of 1/2 log base 3 of x? What's the first part of that? Let me give you a hint. The numerator is 1, okay? I want you to tell me what to put in the denominator for derivative of 1/2 log base 3 of x. Don't lose the 2. That goes there. Part of the denominator, right? Now, what's the derivative of any log? What was the derivative of this one? 2 to the x. Okay, derivative of that was the exponent. Okay, sorry. Here's a log. Here. Derivative of the log is 1 over the thing. So this would be, okay, the 2's there. What's your argument for the log here? X. So the x is there. Now I left a blank because something else goes in there because this is a different base. And what goes there? The ln log, the natural log, I can't write, of 3. Okay? That's ugly, but it's there. Okay? That's the first part. Minus what goes in the second part here, based on what we just did. 1 over natural log of 3 times x plus 5. Now, I don't know the best way to write that. Possibly putting both of those in parentheses. I'm really tempted on something like that to put I know the book doesn't like this, x plus 5 in front, log 3. That way you don't think that it's 3 times x plus 5 or something like that, okay? But I bet you they do it something like this. So that should be derivative there. Let's see what they got. They have, for the first part, 1 over 2 log 3 x minus 1 over log 3, and they put them in parentheses times x plus 5. Now they took it one more step, okay? And I'm not completely sure why they did this, but they did. Because now they have a difference in 2 fractional forms. Let's get the least common denominator. And what is the least common denominator between 2 log 3 x log 3 and x plus 5? Least common denominator. I'll write it up here. Certainly there's a two in it. Certainly there's a log 3, natural log of 3 in it. Okay. Certainly there's an x in it. I'm going to start putting things in parentheses. And there's also a x plus 5 in it. Okay? Now, the numerators, that's another issue. What have I multiplied this denominator by to get this new least common denominator? What's the difference in this one and that one? What factor? X plus 5. So that has to go in the numerator here, because if you multiply the denominator by x plus 5, you've got to multiply the numerator by x plus 5. Why? What's x plus 5 over x plus 5? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value. Okay? Then we have a minus here. And what's in this denominator that wasn't in this one? 2 x. Okay. So let's simplify that numerator. Well, first thing I'm going to do to simplify it is remove those parentheses, because they're not really doing anything but getting in our way, and they're not changing any signs or anything. So what we have up top is a 5 minus x, right? And what we have in the bottom is 2 log 3, and I'm real tempted to multiply those together. I don't know if they do it in the book, but it seems like that would be a little simpler to write. X squared plus 5x. You don't have to do that. X times x plus 5 would be fine too, but that appears to me the simplest way to write it. What did the book do? They left it as x times x plus 5. So 5 minus x over 2 log 3 times x minus 5, x plus 5. Okay. So they just chose not to multiply these two together. Both of those are perfectly correct answers. In fact, this is a perfectly correct answer. That's a perfectly correct answer. okay? It's just that they're simplifying it somewhat and sometimes not, okay? So that's where you go from there. All right, so let's see how they did their answer. You can apply theorem 3.15 to find the derivative of the function. So y prime is d by dx of that thing that we were talking about. That's this form right down here, the second form of y that we wrote down. And then to take derivative of this, it has a 2 in the denominator, and because this is a different base, it has a natural log of 3 in the denominator, and then derivative of any log is 1 over the argument, so that would be 1 over x, okay? The 2 is in the denominator, the log 3 is in the denominator, and 1 over x in the denominator. Derivative of x is 1, so that's why the numerator is just 1. Minus, again, nothing in the numerator except 1 over natural log of 3 because of the base, and x plus 5. I'm writing it that way because I know that's how the book wrote it, okay? So let me, that was our thought process. Let me erase this so you can see how they thought, which was exactly the same way. The 2's in the denominator, the log 3's in the denominator because that's your base. I think of this, since this is subscripted here, put it in the denominator, natural log of whatever the base is. And then the log of, the derivative of a log is always 1 over the argument, and that's 1 over x. So that's what put it down there. Same thing here, d by dx here, because this is a different base, and that's a subscript, put the log 3 down there, and then the derivative of the log is always 1 over the argument. Now, chain rule would have us do derivative of this and derivative of that, but both of those are 1. So nothing in the numerator but that. So this problem, even though it's in the chain rule section, actually didn't even use the chain rule at all, okay? I don't think anyway. It just used the proper principles of logarithms. All right, any questions on that? Oh, and then they rearrange it to have the form they like. They didn't show you the individual steps, but that's how they did it. Least common denominator was this, and then the numerator for this part would be x plus 5, and the numerator for the second part would be 2x, and that's with a minus sign, so that's what gave you a 5 minus x. Any questions? All right. They end the section with a summary of differentiation rules. Do we have a few? Really looks like we do. General differentiation rules, and I don't know if you can read this from where you're sitting because the print is pretty small. Let C be any real number, N be any rational number. We used to have it being integers, at one time even positive integers. Now we're letting it be any rational number. Let U and V both be differentiable functions of x, and let F be a differentiable function of U, okay? They don't have one of V. If you did, that would be probably a G or something like that. And let A be a positive real number, but not equal to 0. Okay, so C is any real number, N is any rational number, U and V are differentiable functions of x, F is the differentiable function of U, A is any positive real number, not 1. Okay, so the constant rule. Derivative of any constant, any real number constant, including 0, positive, negative, fraction, decimal, rational, irrational, derivative of any real number is 0. Okay? Then the simple power rule, okay, they're all fairly simple it seems like, is derivative d by dx of x to the nth would be n. Now remember, n is any rational number, n times x to the n minus 1. You just take the exponent, multiply it by the coefficient. Here the coefficient was 1, so that would be n times 1, which is n times x, and then reduce the exponent by 1. Okay? And a ramification of that is d by dx of x is 1, because the exponent is 1, the coefficient is 1, 1 times 1 is 1, and reduce the exponent by 1, you get x to the 0. And what's x to the 0? 1. Anything to the 0th power is 1. So that's why that's just simply a 1. Constant multiple rule. Again, c is any real number. d by dx of cu would be c times d by dx of u, or derivative of u. But u was a differentiable function of x, so we'll just put u prime. Sum of the difference rule, d by dx of u plus or minus v, where those are both differentiable functions of x, would be u prime plus or minus v prime. The derivative of a sum or a difference is the sum or the difference of their derivatives. The product rule. Whoa, that's a little different. Now remember, u and v are both differentiable functions of x. So d by dx of u times v would be one of those times the derivative of the other plus the other times the derivative of the one. It doesn't matter which one you start with. Not for the product rule. You could do derivative of u plus v plus u times derivative of v. It doesn't matter which order, doesn't matter which order you multiply them, which order you add them. Those are both commutative properties. I can't think of my word here. Okay, so that's your power rule. Your quotient rule, the order does matter. Okay, d by dx of the quotient of two differentiable functions of x, okay, would be, and this is where my Indian student friend helped me get a nice little mnemonic device here. Low d high minus high d low over low low. Okay, that to me is the easiest way to remember this. I used to just remember the denominator times derivative of the numerator minus the numerator times derivative of the denominator over the denominator squared. Okay, that's a lot of words, and it was easy to forget which came first. But low d high minus high d low over low low, if you just remember to start low and go from there, everything works. Okay, order matters in that. Okay, it doesn't matter the order you multiply these, but subtraction is not commutative, and of course v prime or v squared does. Okay, chain rule. If you have d by dx of f, which is a function of differentiable function of u, use the differentiable function of x, then d by dx of f of u would be derivative of f with respect to x, that's f prime of u, evaluated at u, okay, then multiplied by the derivative of the inside, okay, u prime. But again, the order doesn't matter. If you prefer to do a u prime first and then derivative of f of u, just remember when you're taking f prime, it's always of u, not of u prime, okay? So the order of that multiplication doesn't matter either. The general power rule as opposed to the simple power rule, and again, it's pretty, this is with x being your base, this is with u being the base. Okay, so the general power rule, d by dx of, but remember u is the differentiable function of x, and n is any rational number. So, and that's positive, negative fraction, or a decimal, rational number, okay? N times u to the n minus 1 times u prime. And again, if you want to put the n times u prime times u to the n minus 1, that's fine too, or u prime times n to the. The order of multiplying doesn't matter, but that you get all the steps in there, that does matter. And then your trig functions, d by dx of sine is cosine, d by dx of cosine is minus sine. d by dx of tangent is secant squared, d by dx of cotangent is minus cosecant squared. d by dx of secant x tangent x, d by dx of derivative of cosecant x is minus the cosecant times cotangent. And then my favorite of all time, d by dx of e to the x is e to the x. That's what makes it such a powerful thing. These are trig functions, these are your exponential and log functions, okay? And on the other hand, all right, let's go on and do the other powers. If you do a d by dx of a to the x, that is a power, so it's going to have an a to the x in it, but then you multiply it by the natural log of a. See, this is a different base from e. So So you do the derivative the same way as itself, but then you multiply it by the natural log of a. When you're taking the derivative of log x, that's 1 over x. Or if you're taking the derivative of log some other base, not the natural log, but some other base of x, then it's 1 over x. That part's the same, just like here, 1 over x. But you have also 1 over log a. And again, I remember this here. The a is in neutral position, normal position, so it's just multiplied by log of a. Here the a is subscripted, so put that log a in the denominator. That's how I remember it. You don't have to remember it that way, however you want to remember it. But the derivative of the log is also always 1 over the argument. But if this log is not the natural log, then put the base down here. Natural log of the base. Any questions on those? Okay. That ends section 3.4. Except for your homework exercises, which I know you won't know and love, okay? Any of the odds 5 through 11, they're all at Calc Chat. 5's also at Calc View. Any of the odds 13 through 31, they're all at Calc Chat. 13's at Calc View. Any of the odds 33 to 49, they're all at Calc Chat. 35's at Calc View. Any of the odds 51 to 55, they're all at Calc Chat. Any of the odds 57 to 71, all at Calc Chat. 57's at Calc View, excuse me. Any of the odds 73 to 93, they're all at Calc Chat. 73's at Calc View. 95's at Calc Chat. Either 97 or 99 are at Calc Chat. Any of the odds 101 through 107 are at Calc Chat. 109 through 115 are at Calc Chat. 111's at Calc View. And there's some famous curves here. 117 is a semicircle, very famous curve. That's at Calc Chat. 119 should be at Calc Chat. And then any of the odds 121 through 127 should be at Calc Chat. 129 and 131 should be at Calc Chat. Any of the odds 133 to 147 should all be at Calc Chat. 133 at Calc View. You can explore doing 149 and or 151. They're both at Calc Chat. You can think about doing 153. It should be at Calc Chat. 155 should be at Calc Chat. 157. Then you choose any of the odds 157 through. Whoa, they keep going, don't they? I say 167. Any of those odds, they should all be at Calc Chat. 169 you can think about doing. It should be at Calc Chat. There's 171s, even in odd functions you can do those. That one is also at Calc Chat. 173 or 175 should both be at Calc Chat. I've got a sore throat, sorry. 177 or 179 should be at Calc Chat. Then there's a couple true false, 181 and 183 should both be at Calc Chat. And it's up to you if you want to do any Putnam challenges. They are pretty life-affirming. No, they're tough, okay? They can be. All right, so that's up to you. So let's move on to section 3.5. It'll get here in a minute or two, I think. Here it comes. Okay. Let's go from current slide. Still in chapter 3, which is differentiation. 3.5 is implicit differentiation. So far, we've been given functions. Very nice, regular functions. You might not think they were, but as y is equal to some function of x. Y is equal to some function of x. Now, sometimes that function of x can be a little hairy, but it was always y is equal to some function of x. Take the derivative of y. using the rules we just talked about. Now we're going to do your x's and y's are going to be all mixed and mingled in your original problem, and you have to take dy dx. That's called an implicit differentiation. Explicit, you get y as a function of x, just do the differentiation process to the right-hand side. Now you've got to do both sides, okay? Objectives here is distinguish between functions written in explicit and implicit forms. Okay, I've just sort of given a rough description of it. We'll do a little more fine descriptions a little bit with that. We'll use implicit differentiation to find the derivative of a function when it's all mixed up with the independent and dependent variables. And we'll find derivatives of functions using logarithmic differentiation. Now you say, hey, we just did that. Oh, we're going to do it even more so. Okay? So let's first talk about the difference between implicit and explicit functions. Most functions so far in this chapter have been expressed in explicit form. Y is equal to blah, some function of x. This is one right here. Y is equal to 3x squared minus 5. Notice the left-hand side is y and y alone, and the right-hand side are functions of x and x alone. There's no y's over here, no x's over here. This is an explicit function of y. Y is a function of x. Variable y is explicitly written as a function of x. Real easy to take its derivative. What would it be? What would be the derivative of that y? 6x, exactly. 6x, you did it. No, 6x. Okay, got it. All right, some functions, however, are only implied by an equation. For example, this is an explicit function, okay? But this one is not quite so explicit. xy is equal to 1. Here we have x's and y's here, and here we have neither over there. But this one can be written as an explicit function by dividing both sides by x, and that's what they did here. They went about it backwards here, but this was not an explicit function of y, but this is. But it's the same function, you know, but this is an implicit form of that function, okay? Now, to find dy dx for that equation, you can write explicitly the y as a function of x, and then differentiate. And what would be your, okay, there's your form. Y is equal to 1 over x. You get it by dividing both sides by x. Now, what would be your first step to take the derivatives of it? Yeah, write it as x to the minus 1, because I like it in exponential form rather than division form. And then what's the derivative of x to the minus 1? Negative 1 times x to the minus 2. Reduce that simple power rule, okay? And then, if you wanted to, if you don't like having negative exponents, you could then rewrite this as minus 1 over x squared. That second part, in my mind, is not necessary. The book likes to do it just about every time. That strategy works whenever you can solve the function explicitly. Here you could, okay? You cannot, however, use that procedure when you're unable to solve y as a function of x. I think one of those must be coming. For instance, how would you find dy dx of this equation? Anyone want to make a guess? Okay, yeah, that might be a good first step, is try to isolate the y's on one side and the x's on the other. Now, I would probably move these over here and this one over here, and have 2y cubed plus 4y minus 4y is equal to x squared minus 2. But then try to get that y out of there explicitly. You can't do it. So that first step did not help you get a derivative. It It isolate or separate the x's and y's, but it didn't have to get a derivative. In this equation, it's difficult to express y as a function of x explicitly, so to find the y dx in one like this, use what we call implicit differentiation. Now, I think they're going to tell you what that is on the next slide. Let's see if they do. To understand how to find the y dx implicitly, you must realize that differentiation is taking place with respect to x. Remember that, with respect to the independent variable. This means that when you differentiate terms involving x alone, you differentiate as normal. But when you're differentiating with respect to y, a term with y in it, you do take the derivative of that term, but then you have a dy dx because of the chain rule. You must apply the chain rule because you're assuming that y is defined implicitly as a differentiable function of x. That's always your assumption. Now, if that comes up being a wrong assumption, you can't do it, period. Okay. So, this is pretty easy. Okay. What's the derivative of, with respect to x of x cubed? 3x squared. You know that. The variables agree. You take it with respect to x, take the derivative of x, okay? And that's all. You do 3 times x squared. If you wanted to, you could say dx dx, but dx dx is 1. Dx over dx is 1, okay? So you don't usually write that, okay? Now, what about here? What would you do? Yeah, you first take the derivative with respect to y, and that would be 3y squared. That's the first part. But then you have to turn around and chain rule. What does the chain rule tell you to do? Take the derivative of the inner function, which is y, dy dx. Okay? Does that make sense? Not really, huh? Okay. It's just the chain rule. Understanding this y is a function of x, so and I don't know if you found this as being helpful. This is like saying derivative of u to the n, where u is y and n is 3. Derivative of that would be n times u to the n minus 1 times u prime, right? We did that for the general chain rule. But remember, the u was y and n was 3, so it would be 3y squared. Okay, that's this part. Then u prime, u was y, that's dy dx. Okay, so there's, like they're saying here, this is taking derivative with respect to the independent variable, but you're taking it of the dependent variable, so you have to use the chain rule. For that last step, you always have a dy dx. Okay, and it's usually dy dx, or whatever your dependent variable is. That's how you take a derivative implicitly, okay? We'll leave it like that. Okay, let's see if there's a C here. All right, what would you do here? Dx of x would be 1, okay, plus, and dx of 3y, 3 dy, exactly, 3 dy dx or 3y prime, exactly, okay? Because the second part is a function of x, so you have to turn around and take the chain rule. So you don't have to do this here because dx dx is 1 also, so it'd be 1 times 1 is 1. This is 3 times derivative of y with respect to x. Just a chain rule, sort of in a hidden form. Does that make sense? Okay. Here's one more. Oh, what do we do with that? Help me. What rule would we use? We'll use several. Okay, how do you mean by that? Okay, derivative of x is equal to 1. X doesn't equal 1, but derivative of x. Is that what you meant? I thought so. Okay. Now, what does that have to do with it? Say again? 1 times what? Whoa, whoa, whoa. Okay. Back up a minute. There is another rule that you're skipping. What does x y squared mean? What's the relationship there? Say again? Multiplied. And what's the answer to a multiplication problem? A product rule. You got to do the product rule. So don't forget the product rule. How does that go? Say again? X times of y squared, which would be, right? What else? 2y, y prime. Remember, dy dx. Did you say that? Oh, okay, I couldn't hear. X times 2y times, okay, it takes them a while to get that. They're going to get that in the next step, okay? Plus what? Second part of the chain of the product rule.
Y squared plus the derivative of y.
And what's the derivative of x? 1. So that'll be just plus 1. Well, they write it down like that too. Good for them. Okay. So we'll pick up and do our writing from here. Okay. So this is going, ooh, let me get my pen back. Let me get my pen back. There we go. Okay. This will be x. And what's d by dx of y squared you said before?
The derivative of y squared is 2y.
2y dy dx. Excellent. Okay. Plus y squared. And what's the d by dx of x? 1. Exactly. There's your answer right there. That's, you do the product rule first, and then you do, in effect, the chain rule second. Okay? The second part doesn't have a chain rule part, but the first part does. Okay? So is it all right for me to erase? I'll let you finish writing. Is this making sense so far? Okay? What's that? I still can't. Huh?
It's about to get more complicated.
Oh, always. Okay. You start easy, and then when it gets really hard to say, and this will be left to the student. Okay. That's standard textbook writing procedure, and instructor procedure as well. Okay. If it gets too hard, I don't want to explain it. You figure it out. Okay. The only difference, I like to put y prime rather than dy dx because it's just much easier to write. But there are some problems with it. Sometimes you forget about that y, the prime being there. This is hard to forget about the d by d being there. All right to erase? Okay. Everybody? Okay. And then what they do next is x times 2y dy dx. Same thing we did, except they put parentheses around it. And this is y squared times 1. We just put the 1 times 1. And then they take one more step to write 2xy dy dx plus x squared. Done. Done. Implicit differentiation. Okay. Let's see if there's an E. No, there's not. So we move on to implicit differentiation, which is what we were just doing, but now it's going to give you the guidelines. So differentiate both sides of the equation. This is if you have an equation here. All we had before were expressions. Okay, now we're going to have an equation. Differentiate both sides of the equation with respect to the independent variable. In most cases, it's going to be x, but not necessarily. Okay, once you do that, Differentiate as you read it, okay, with respect to x. Once you've done that, then collect all the terms that have a dy dx on one side, they say the left side, whichever side is more convenient of the equation, and move all other terms that don't have a dy dx, they can have y's but no dy dx, move them to the other side. They said the right, I'd say whichever is more convenient. Now, if all your terms on one side or the other have dy dx in them, then you can factor out the dy dx out of everything, they say on the left side or whichever side that winds up being, and then solve for this by dividing whatever you had left. It's a lot easier doing, I think, than reading. So let's try doing it. Okay? Find dy dx from this equation, not just an expression, equation. But guess what? This expression is just, this equation is expression on one side, expression on the other side. So let's go for it. What is dy dx of y cubed? Help me, somebody. 3y squared dy dx. You're absolutely right. Plus, and what's the dy dx of y squared? Say again. 2y dy dx. Okay. How about the next one? What's the dy dx of minus 5y? Minus 5 dy dx. You got it down. Okay. How about of minus x squared? Minus 2x. How about of, there's the equal sign, how about the derivative with respect to x of minus 4? Nope. 0. Derivative of a constant is 0. Perfect. Okay? Now they like left and right sides. You already have all your dy's on the left, so let's just get anything without a dy to the other side that happens to be the right. How would you do that? Second? Add 2x to both sides. Okay, that sounds like a winner to me. Okay. Now I think I'll do it in gory detail here. 3y squared dy dx plus 2y dy dx minus 5 dy dx is equal to 2x. Okay. I just wrote it down one more time. Now, what they say do next? What are you looking for? Dy dx. So what you reckon you're going to do? Factor it out, exactly. So let's factor out dy dx from every term on the left. And we got rid of all the terms that didn't have it in there, so that's every term on the left. What do you have left? 3y squared plus 2y minus 5 equal 2x. And guess what we do now? Solve for that. How? Not that hard. Once you see it, you'll go, what's that? We want to isolate this. How do we do it? Divide both sides by 3y squared plus 2y minus 5. 3y squared plus 2y minus 5. This term goes out here, and you have dy dx is equal to 2x over 3y squared plus 2y minus 5. That's it. That's done. Now, there may be some part of your innermost being that is saying, well, can you factor this? And if you can do it, if that makes you feel better, that's fine. But it's not going to divide out anything, so it's just, I hate to say a wasted use of time, but maybe it gives you practice factoring. But I don't even think it's factorable, so I wouldn't even, yeah, it may be factorable. I think it is. But what's the point? it's not going to simplify it any. If you did, I'm just glancing at it. It looks like it could be factorable. Okay, but let's see if they do. No, they don't. They just leave it just like that. Okay. Now, want to watch how they did it, or do you need to a little more time copying this? Okay, take your time. While y'all are doing that, for people who did come in a little bit later, I'll say this again. This week is a strange week for me, so my office hours are a little screwed up. Tomorrow I won't be on campus from 9 until around 12ish, maybe a little before, a little after 12. So any office hours I may have had between those, I won't be in my office then because I've got a doctor's appointment. Okay? Then Thursday, I won't be on campus at all until late in the day, probably sometime after 4. My meeting in Tuscaloosa, I think it's supposed to be over with by 3:30. So, or whatever time they get over, I'll be coming back by here. I'll come to campus and stay until 6. So I will be on campus Thursday, but it'll be late in the day. I don't know what time I'll get here, but I'll be here until 6. I'm guessing 4:15ish, 4:30ish, something like that, until 6 o'clock. Okay, yeah.
At the bottom, where the will be divided by 3y squared is 2y minus 5.
Right.
We did that just to isolate the dy minus 5.
Yeah, that's what you're looking for, so you want that by itself. Okay? That's why you did it. Exactly. Okay? So, all right to erase? Okay. Let's see how they did it. Differentiate both sides of the equation with respect to x. So they wrote that in, which was really useful, right? All right, so let's do it. D by dx of y cubed would be, okay, they split them up. All right, if you want to write extra steps, do it. It's fine, okay. D by dx of y cubed plus d by dx of y squared minus d by dx of 5y minus d by dx of 2x is equal to d by dx of minus 4. If that helps you see it, by all means do it, okay. So what's d by dx of y cubed? 3y squared. Chain rule, dy dx. And that's what you got there. The derivative of the second term here, 2y times dy dx. The third term, minus 5 times dy dx. And the fourth term, minus 2x. Derivative of the right-hand side is 0, because the derivative of a constant is 0. Okay? Now, you have taken the derivative of every term on both sides of the equation. Now what you want to do is separate the terms that have dy dx in them on one side and those without dy dx in them on the other side, which simply means moving the 2x to the other side. So that becomes 3y squared dy dx plus 2y times dy dx minus 5 times dy dx. Those are the terms with dy dx in them is equal to 2x. Okay? Now you want to factor out the dy dx so you can isolate it. Okay, so first factor it out, and that's dy dx times 3y squared plus 2y minus 5. That's equal to 2x. So don't forget the right-hand side. Okay? And then because you want to isolate the dy dx, you want that by itself, then you divide both sides by 3y squared plus 2y minus 5. And that gives you that. Dy dx is 2x over 3y squared plus 2y minus 5. Done. Complete. You isolated, you found what dy dx is. You did it implicitly. You could not solve that equation for y and then take a derivative. Implicit, though, was pretty easy. Now, to see how you can use that implicit differentiation, consider the graph shown here. This is the graph of this equation. That's the graph of an equation. would you say that graph represents a function?
No.
Why not? It fails the vertical line test pretty miserably in several places, okay? But it is a graph of an equation. But guess what? You can still use that graph to find where dy dx is equal to 0 here, and that's the only place. You can plug in values. You see that y is not a function of x. Even so, the derivative found in example 2 gives you a formula for the slope of the graph of a tangent line at any point on the graph. The problem is finding the points on the graph, okay? Because you have to manipulate both x's and y's at the same time. You just have to do some figuring, okay? For instance, it's pretty easy to put a y equals to 0 in here, because then all these terms will be 0, and then you have minus x squared is equal to minus 4. It's pretty obvious x has to be either plus or minus 2, okay? Here's the plus 2, there's the minus 2, and y is equal to 0, okay? Now, I don't know if any others are easy. How about when x is equal to 0, then this thing is equal to minus 4. Like I said, this was, I'm pretty sure is factorable. Factor out a y for sure. Y is equal to 0. Then x is going to have to be, yeah, you can go through and do your various points like this. When x is equal to 0, y is equal to why in the world they didn't put an ordered pair there? That's minus 3, or looks like minus 3, 0. But according, 0 minus 3. But I don't think that's true. No, because at 1 minus 3 is a point on the graph, so this is something a little bit more. So anyway, you can find various points. But at the point 1, 1, where y is equal to 1, well, you can plug things in there, your slope is undefined, because it's a vertical slope, both at minus 1 and plus 1. So you have various things you can do, but if you have points you know are on the graph, like this one and that one, they didn't put this point on the graph, they just put the x value of it, then you can use the formula you got to give you your derivative. And the reason 1, 1 doesn't work is when the denominator is 1, when y is 1, your denominator is 3 plus 2, which would be 5, minus 5 is 0. Nope. And minus 1, 1 won't work either, because again, your y would be, your denominator would be 0. They didn't tell you, but also here, that the slope would be undefined, that would be undefined, because it's vertical lines. Okay. But they didn't do all those points. So there is, it is possible for you to get information about points on the graph even if it's not a function. And that's why it's not a function of x. You can still differentiate and do other things with it though. Now, it's meaningless to solve dy dx in an equation that has no solution points. For instance, will this ever have a solution? X squared plus y squared is equal to negative 4.
No.
Why not? What's that?
That's what it says. It has no solution points.
Why is that? How do you know that? Because guess what? X squared, if x is a real number, any real number in the world, when you square it, what is it? Never negative. Could be 0, but never negative. How about y? If y is any real number and you square it, it's going to be, yeah, same. Either positive or 0, but never negative. So can you add two positive numbers together, even if one or both of them are 0, and get negative 4?
No.
Never! So this is a ridiculous problem. Don't try doing an implicit differentiation in it. makes no sense. The problem is ill-posed, okay? It doesn't exist. There is no solution to that, so why try to get a derivative or anything else? It makes no sense. If, however, a segment of a graph can be represented by a differentiable function, then dy dx will have a meaning as a slope at each point on that segment. Recall that a function is not differentiable at two places. Points where the vertical tangent lines, not differentiable there, and points at which the function is not continuous, like there, okay? So those are the two things that you worry about, okay? But anywhere else, it should be differentiable. All right, so let's do example 5. Determine the slope of the graph of this thing here. 3 times x squared plus y squared, in parentheses squared, is equal to 100xy. Oh, one of my favorite functions of all, or equations of all time. Okay?
We skipped some.
What's that?
We skipped some.
It's what?
We skipped some.
Oh! It did, didn't it? Shame. Yeah, it went from example 2 to example 5. Thank you for catching that. I would have if I glanced at the book. So let's first do example 3, okay? If possible, represent y as a differentiable function of x, okay? X squared plus y squared is equal to 0. Can you express that as a differentiable function of x?
Are you asking can x squared plus y squared equal 0?
Right. When?
No.
Never? Oh, one place it can. Second?
0, 0.
Yeah, 0. Yep, it's equal to 0. Any other points? No. Okay, so can we represent y as a differential function of x at a single point? No, you need, I mean, what's the slope of that point? Okay, you don't even have a function, a graph there. It's just a single point. It could be here, you know. So no, you can't differentiate, or you can't represent y as a differential function of x, okay? That's a single point, so it does not define y as a differentiable function of x, okay? That's A. Not, okay? B. X squared plus y squared is equal to 1. Okay? Can you represent y as a differentiable function of x? Mm-hmm. How? Okay, well, okay. Wait a minute. Okay, let's try to do it up here on the first one. X squared plus y squared is equal to 0. I just had you think through it before. Let's actually try to do it. Let's actually try to solve for y. So what would be your first step? Yes, okay. You subtract x squared from both sides, and that would give you y squared is equal to negative x squared. Now right there, bells and whistles and lights and flashing red lights should say, warning, hey, this doesn't make sense. But if you tried, then you would take the square root of both sides, right? That'd be y is equal to plus or minus the square root of minus x squared. And then surely bells and whistles and flashing red lights should go off and say, hey, you can't do that, you know? You cannot take the square root of a negative positive number. You can take it of 0 and that's all. So 0, 0 is a single point, the only one. Okay, now let's try that same technique over here. Solve for y. First step. Subtract x squared from both sides. And what does that give you? 1 minus x squared. And then square root of both sides, so y is equal to plus or minus the square root of 1 minus x squared. Now, it says, if possible, represent y as a differentiable function of x. This is not a differentiable function of x because, as you pointed out before, give me an x. Some x's won't work at all, but for instance, x equals 0 will work fine, right? But then when x equals 0, you have y is equal to either plus or minus 1. Wait a minute. For any given x, you can only have one value of y, right? So you can't, this is not a differentiable function. That's a differentiable function, or that's a differentiable function, but not both. Okay? So you could have either one of those. So either either that one I meant to do wipe out the minus sign, or I can't write. Both of those are differentiable functions of x. On limited domains, x can be any less than minus 1 or greater than positive 1. So these are both differentiable functions of x when x is between minus 1 and 1. Anything greater on either direction, and this gets to be a negative number. So anything between minus 1 and 1, yep, that's a differentiable function. Now, does anyone know what this is an equation for? Don't miss the forest for the trees here. Anyone know what shape that function graph has? A circle of, whoever said it, radius 1. That graphs like this. Okay? It's an ugly circle, but you know that's supposed to be it. Is that a function? No, vertical line test fails. However, I'll do a couple of different colors. Pick a color other than black. Red, okay? Let's let red be that one. Here's a function, okay? That's a perfectly good function, isn't it? This goes up to 1 here. Give me another color. Blue. Carolina blue or darker blue? Carolina blue, all right, okay. Here's another function. That's a perfectly good function. So either one of those is a function. Either, I didn't circle. This is Carolina here, okay. All right. This one or that one are both functions. Not both, either or, okay. That's why there's a little or in there. All right. Make sense? Okay. So yes, you can represent y as a differentiable function of x. In fact, in this case, two differentiable functions of x. Okay. So let's do the c then. Okay. Well, let's go back to black for my c. That's yes in Spanish. Okay. And I don't need equal sign there. That is x plus y squared is equal to 1. Can that be written as a differentiable function of x? Yeah, how? Second? Okay. Okay, yeah. Okay. That's a specific point, but can that be written as a function of x? What was our technique before? Solve for y. So what would you do? Subtract x from both sides, and that would give you y squared is equal to 1 minus x, and then square root of both sides, and that would be y is equal to, but plus or minus the square root of 1 minus y. Guess what? That's not a function, because for any value of x that will work, And not every value will work. Like x can't be 2 or 7 or 4.5 or anything greater than 1. But x can be anything less than 1. Minus 15 would be fine. Because 1 minus a minus 15 is 1 plus 15, which is 16. That would be a 4. Okay? But you can't have a plus or minus one or the other. Okay? Now, again, don't lose the forest from the trees here. Remember, x can't be, has to be anything less than or equal to 1. So let's just call that 1 out there. What kind of a shape is this? Especially if I wrote it this way. X is equal to y squared. No, 1 minus y squared. That would be it, wouldn't it? Come on, give me my eraser. Or you could write this as minus y squared plus 1. Right? Wouldn't that work? If you solve for x here, which you normally we don't, but you just subtract y squared from both sides, or write it this way. Now what is that basically the shape of? A parabola. But this parabola is not standing up like this, it's like this. So that would be a parabola opening toward the negative, so that would be a parabola like this, or like this, because these 2 points, 0, 1, and 1, and 0, minus 1 are both on it, right? But you see that's not a function. So if we do the same colors as before, let me also, before I do that, write this as y is equal to square root of 1 minus x, or minus the square root of 1 minus x. Okay, then doing the same colors as before, the red would be the upper side, and the Carolina blue would be the lower side. Okay, both of those are functions of x, but only one at a time. Okay, and that's basically a square root function, half of the square root function, half of the sleeping parabola. Okay, so both of B and C can be written as functions of x, but you have to restrict domains and ranges to make them functions. Okay. All right. That makes sense? And this one will say x, ooh, let me get back to black. Okay. Up here in B part, thought I went back to black. Minus 1 less than or equal to x less than or equal to 1, and down here x is less than or equal to 1. Okay, in both of those circumstances. Okay. So that was equation example 3. Ready for example 4? All right. Now y'all keep up with my time too. How are we doing? Second? 15 minutes, excellent. Okay, for some reason my pen's not writing well. Example 4. And by the way, example 4, even though it's not on the slide set, you can go to larsoncalculus.com and see an interactive version for this type of example. So here's the problem. Determine the slope of the tangent line. So determine, let me do this. Determine the slope of the, this all comes down here, tangent line to the graph of x squared plus 4y squared equal 4. At the point root 2, comma, minus 1 over root 2. Interesting the way they write that. Okay? Now, time out. I am a cynic, okay? I don't want to start off doing a problem just assuming they gave me a problem that makes sense. They may say x squared plus y squared is equal to 0, or x squared plus y squared is equal to minus 4. I'm not going to take off and start doing that until I make sure that makes sense, right? And neither one of those did, especially finding a derivative, okay, or even finding a point on the second one, okay? So I want to make sure that this point is indeed on this curve. So let's take square root of 2 and square it. What does that give you? 2. 2, okay? Let's take 1 over, or minus 1 over the square root of 2 and square that. Is what? Okay, yeah, it would be 1/2. So 4 times 1/2 would be 2, and 2 plus 2 is, hey, doing high level math today. 2 plus 2 is 4. We got it. Okay. So we made sure that was on the curve, and it is. So I'm happy now. Wasn't before, but I'm okay now. Okay. Now, what we want to do is determine the slope of the tangent line. Now, how are we going to find the slope? What's the Jesus answer? Huh?
Point slope formula.
Okay,
You use
little.
point slope formula.
Okay, I need to find the slope before I can use the point slope formula. Okay,
We can't put the equation in the correct format, like y is equal to mb.
I guess I could, but what? Okay, let's think back. Go back in time a little bit now. How do I find the slope of a function or of an equation? What's the Jesus answer in this course? Take a derivative. That's going to give you a slope, right? dy dx is a slope at any point, right? So we need to do that. But what kind of function is this? Now we could do, as you said, try to solve it for y first, and then take a derivative. So much easier to use, what did we just study about? Implicit differentiation. Let's do it. What would that be? 2x plus 8y excellent. I'm going to put y prime because I'm lazy. Is equal to 0. Got it. Now what do we do? Isolate the y prime, right? Okay, how do we do that? Subtract 2x from both sides. I think that may have been what you were saying, right? Minus 2x, good deal. That gets rid of this, and we have 8y prime is equal to minus 2x, and then what? Do what? Do what? I can't hear. Excellent. Divide both sides by 8y. Okay, my hearing's so terrible. Okay, my wife says it's selective hearing loss, but that couldn't be true. Okay. Hey, you know, it's not that funny. Okay. All right. Y prime is equal to negative. Well, let's simplify that a little bit. Okay. How about negative 1/4 x over y? Right? Is that what you get? Okay, now, if indeed, and we already have shown this point is on that curve, so let's plug that point in there and find the slope at that point, right? So let me call it m at this point, root 2, negative 1 over root 2. The slope there is going to be negative 1/4. And then what's your x? Root 2 over your y. A negative 1 over root 2. Okay. Now, a negative times negative are positive. You got two negatives, that becomes positive. I'm going to get rid of those. Now, when I divide a fractional form like this, what do you get? Root 2 divided by 1 over root 2. How do you do that? Invert and multiply. That's root 2 times root 2 over 1, which is 2. Okay? So this is going to be 1/4 of 2, and what's that? What's that? 1/2. I thought that's what you said. Okay. All right. 1/2. There's your slope at that point. Right? Now you got the slope and a point. So now we go to where Houston was trying to take us earlier. And what's that? Point slope formula. And what's that? It's messy, but what is it? Maybe it. Weren't you telling me to use it? Oh, then tell me what it is. You don't expect me to remember, do you? Huh? Y minus y1 equal to m times x minus x1. Thank you. So I don't have to remember that kind of mess, okay? So what's this? Y minus, and what's your y1? Is. Second? Negative 1 over root 2. I really don't like that. Okay. Is equal to m. We just discovered what m was. What was our m? 1/2 times minus square root of 2. Okay, now that's pretty ugly, isn't it? All right. All right, I'm going to simplify that just a little bit. I'm running out of room. Y plus 1 over root 2 is equal to 1/2 x minus root 2 over 2. Right? Now, still awfully messy. Let's see if they leave it in that form. Come on, don't they finish the problem? Oh no, I'm sorry. Determine the slope of the graph. They didn't say what's the equation. Sorry. Okay, you didn't need to do that part. This is what you would have done. All they said was determine the slope of the graph of the tangent line. There it is, 1/2. That's all you had to do. Thank you very much. Okay, I was going to go on and give you the equation of the tangent line, which is going to smell really bad. I mean, yeah, it wasn't going to be nice. Okay, that is the equation, by the way. It's just not in very pretty form. Okay, all they were asking for is find the slope of the tangent line. We did it. Using implicit differentiation. You could have done it Houston's way. He's a hard worker. He likes to do it the hard way. But yeah, you could have done it that way, but we didn't have to. Okay, how are we doing now on time?
5 minutes.
Second? 5 minutes. Oh, 5 minutes? Oh, good. Okay. So now we can move to example 5. Any questions on this one before I erase? And by the way, you can go to larsonCalculus.com and see the full extent of it. Okay. In fact, I found that sort of interesting because my other text uses that. Oh, maybe they don't use that book. Okay, that website. Okay. Anyway, can I erase? Yay. Okay. So now we're ready for example 5. Determine the slope of the graph of this thing at the point 3, 1. Guess what old cynical me wants to do first? Yeah, make sure these values work. So this will be 3 times 9 plus 1 squared. That would be 300. Is that what you said? Yeah, I like that. And what is it over here? 100 times 3 times 1. Yeah, works. All right, I'm happy to continue. Okay. So I'll erase that mess. I verified that point's on that graph. So again, all they're asking for is a slope, not an equation of the tangent line, but a slope. So how are we going to do that? How? The what? Okay, we're going to do the implicit differentiation, right? Oh boy, how does that go now? At least start it for me. Okay, well, we're just write down 3. That's just a constant. Now, derivative of this thing, that's a chain rule problem, right? And what would that be? Times 2 times x squared plus y squared to the first power times, that's the outer function. Now the chain rule part, the inner function would be 2x plus 2y, second, dy dx, excellent, okay, I can't write, okay, that's the left-hand side. It was a chain rule and various other things, okay, and the right-hand side, oh boy, I didn't leave enough room, did I? The 100's going to be out front, and then what do you have left? Help me, somebody. What rule do we use there? Product rule. How does that go? X y prime. Second. Say that one more time. Oh, is it? I didn't know that. I thought that's what we were looking for to get the slope. Derivative of x is 1, but derivative of y is derivative of y, right? But there's a second part here, isn't there, to the product rule? What is that? Plus y. Why not? That's it. Okay. Y times derivative of x, which is 1. Okay. Maybe that was your one you were talking about. Okay. Now, I'm going to need to string this out a little bit longer to the left here. But I also want to note that here you have a factor of 2 in this term too, right? So that's going to be another. So that's going to be a 3 times 2 times 2. That's going to be 12 out front, right? Times x squared plus y squared times x plus y dy dx. Am I right? That's the left side. Is equal to, I'm going to distribute through 100 xy prime plus 100y. What's that? Okay. We had the 3 that was already there. Okay. The 2 from your exponent. And then this, I can see, has a factor of 2 in it. So I factored that 2 out, and 3 times 2 is 6, times 2 is 12, and that's why this term doesn't have the 2 anymore. I was just skipping some steps there just to confuse the students. I succeeded, right? Okay. Yeah, okay. As always, is a nice feeling. All right, now we got a really big problem here. We got a foiling problem that is a madhouse, but we got to do it, folks. Okay? We have to multiply these two binomials and then multiply by 12. And that's a real pain in the neck, isn't it? But let's do it because we like pains in the neck or other parts of the anatomy. Okay, 12 times. Okay. Let's do the outer first, and what does that give you? I mean, first, I'm sorry. First is what? X cubed, and then do the outers. Oh, I should do the outers like this, shouldn't I? Okay. That way I'll get my smiley face. I like smiley faces, okay? Okay. What does that give you? Plus x squared y prime. Can I write it like that just because I'm lazy? Okay. Now do our innards. What are those? XY squared, right? And then finally do our last, which is y cubed y prime. Okay. And that's equal to 100 xy prime plus 100y. Agreed? And now we got to multiply the 12 by everything. So this is going to be 12x cubed plus 12x squared y prime plus 12xy squared plus 12y cubed y prime is equal to 100 xy prime plus 100y. Okay. I got that set up for you. What do you do next? Can you show me any? Now, if you had said gather like terms, I might be a little more agreeable to that. In fact, what we want is all the y primes on one side and all the non-y everything else on the other side. So let's do that. This will be subtracting 100 xy prime from both sides. Okay, it's from somewhere there. And we'll be subtracting 12x cubed and 12xy squared. Is it out of time? I'm guessing we are we? Okay. Okay, now I get to say. And the rest is left to the student, okay? Unless you want us to finish this next time. Finish it next time? All right. All right, we'll finish this next. Y'all remember where we are and get me back to this point, and we'll wrap this up from there. Okay. Okay. Then let's end this. Wait, before we end that, I do need to give you your homework assignments for this. Let me mark my place here. Where were we? We were somewhere down here gathering the y prime terms. So we're right about there, okay? So, homework exercises here, not too many. I think you can do any of the odds 5 through goodness, why not all 5 through 25? They're all at Calc Chat, 5's at Calc View. And try doing 26 or 29, 27 or 29, they're all at Calc Chat. 29's at Calc View. And then start working on 31 through 37, they're all at Calc Chat. 31's at Calc View. And I think you could probably even try to do 39 or 41, they're both at Calc Chat. 39's at Calc View. And let's hold off there and we'll pick up the rest of those next time. All right, good deal. All right, we'll see you on Wednesday.